everyone, welcome to CMKL Special Talk 2022. Right now you are with me, Pacharapon Saitongyot, or you can call me Far. I'll be the moderator for our talk today. Let me tell you a little bit about our talk series. It's a talk that brings notice speakers to campus each year to provide the CMKL community with different perspectives and topics of thought. And right now, our talk journey has come to the series of 2022, and we are at the episode 7 in the topic of remote sensing research. And our speaker for today is going to talk about this topic. He is our PhD candidate in Electrical and Computer Engineering program of Carnegie Mellon University, CMKL, Thailand. Please welcome Mr.Shaun Stevens. Shaun, hello.
Hello. Okay. Can you hear me? I know you're right next to me, but am I coming through that all right? Thank you for that, Bob. My name is Shaun Stevens, and I'll be giving a little talk on remote sensing and remote sensing research today. So I hope you all enjoy it. Can you see my screen?
Yes.
Okay. Let's go ahead and start from the beginning. All right, so remote sensing research. This talk will be structured. I'll begin with a little discussion on what remote sensing research is at a high level, like the different kinds of remote sensing research, what it's used for, why do we use it? And then I'll go into specifics of what I've done in my research so far. What I have done in my research up to what I'm currently doing, just briefly getting into a little blurb on what my current research is. So my name's Shaun Stevens here at CMKL, and really enjoying it. So what is remote sensing? The gist of it, the basic idea is that you want to learn information, gain information about an object, area, person, thing that you're observing, thing or space that you're observing without actually physically touching it, coming into physical contact with it. And I have physical in air quotes there because while you're not physically touching it in the practical sense or the well-known sense, there is a physical interaction that is occurring. There has to be some sort of physical force acting between you and the target for that information to propagate. And I'll get to, in a moment, I'll get to what those are, but without the generally accepted idea of physically touching something. So you're trying to gain information at a distance, like it's over there, I'm over here, I want to know about it. And it's also finding information at a distance and information through physical objects, such as walls. You want to know what's going on the other side of a wall or in another room, through windows, furniture objects, and in a larger sensing for things like geosensing, natural formations, or things like sonar, water, different natural formations that might block your way. So why use remote sensing? One thing might be efficiency. It might be a more efficient setup to be able to look at something from a distance rather than have all the equipment that needs to be put on it on site, I guess to say. You save space as far as materials needed for wires and whatever needs to physically touch the person. Another thing might be safety. Certain environments are not conducive to people being able to survive very well. And so say you need to like sense the inner workings of a nuclear reactor. That's something where you can't actually put people to go and physically touch it. If you have a remote way of doing that, that's good. Which I don't know if they actually have very many remote sensors that operate with like wireless sensing in and out of a reactor, but or other hostile environments like deep water, volcanoes, that sort of thing. Another reason no other sensing method might be available to you. So one example would be geosensing. When you're trying to do mineral exploration or oil exploration, you need to be able to sense into the ground. It's not like you can take a really eventually, I guess the point is to take a really long pole and really drill down to it. But as far as like finding where that's at and knowing ahead of time so you can make the best educated guess on where you might strike whatever mineral or resource you're looking for. Remote sensing can be used for that. And then the final one is convenience. One might be occupancy tracking. So you can have a remote sensor that counts the number of people in a room. And rather than having someone there, you know, tallying the amount of people going in or having the people have to go and clock in, clock out as they go to do something, it might be much more convenient for them to just be able to walk in, have a sensor at a distance, sense their presence, and then add it to a digital registrar of who was all in the room. So those are a few reasons. Probably think of more. Those are what I have off the top of my head. So remote sensing methods are the mediums by which we accomplish remote sensing. So there's two main ones. There's also a third, which I'll touch on briefly. But the first is mechanical waves. And these include things, mechanical waves, sound, acoustic waves, basically physical wave propagation through physical mediums. So air, solid materials, liquid materials, but through the material. Speech, as I talk to you right now, that's an example of a mechanical wave. The vibrations from an earthquake are an example of a mechanical wave. Vibration in general, in whatever form it might take on, is a mechanical wave. So, and the other medium by which we sense, we do remote sensing is through electromagnetic waves. And so this is things like anything that falls along the electromagnetic spectrum. That can be light. Your eyes are doing remote sensing in a way, sensing using the visible light portion of the electromagnetic spectrum, but also things like radar that use radio wave and microwave portions of the electromagnetic spectrum to sense objects at a distance. Anything that falls along there propagates using electromagnetic waves would fall into that category. And so there's a third one, gravitational disturbances in the gravitational field or gravitational waves. I think gravitational waves are only recently discovered to have existed. Somewhere off in the universe, two black holes collided and we were able to detect them. But other things more practical, I've read about submarines being able to take slight disturbances in the Earth's gravitational field to tell whether or not there's an object above them, another ship trailing above them or not, which is interesting, but also very niche. Most of the remote sensing that is used in industry and in military applications is either mechanical, relies on mechanical waves or electromagnetic waves. So I have those two arrows coming down for signal. That's the important term, is that whatever medium you're sensing through, they carry a signal, and that signal is information about the object or area being sensed that you use to figure out things about it, that you process and use different algorithms to tell, like, okay, what am I actually looking at? And some of those algorithms are very simple, some of them are very complex. Everything is a signal in a sense. The same type of electromagnetic waves used for Wi-Fi are also used for microwaves. Not a lot of people know that, but they both operate at the same frequency. Wi-Fi 2.4 gigahertz, microwaves also 2.4 gigahertz. Funny enough, that's why your signal might flash in and out if you have your router next to your microwave and there's a little bit of radiation leakage. Similarly, your voice and sonar systems are both mechanical waves, similar. And the only difference between these, Wi-Fi, microwaves, your voice and a sonar system, is there's a difference in the signal power, so the amount of energy in the signal shape, like what exactly it looks like. Is it a long continuous waveform? Is it a small burst of waves? And then the frequency composition. So frequency would be things like the type of electromagnetic radiation, microwave versus visible light. Visible light is a higher frequency, or the acoustic analogy would be like a deeper voice versus a higher pitched voice. Those are voices at different frequency, and they have different frequency components. An important thing to note, usually for sensing, we're trying to not destroy the thing we're trying to sense. Like I said earlier, a Wi-Fi router and a microwave operate at the same frequency, but the microwave is using roughly 1,000 times more power. So the router is operating on the order of 1 watt of power. The microwave is operating with a continuous 1,000 or 1 kilowatt signal, or around there, in the many hundreds of watts to low kilowatts. So in sensing, there's two kind of paradigms. There's passive versus active sensing. Passive sensing, you are just listening, essentially. You're just waiting for a signal, and you're just waiting for the signal to come in, and then you receive it. So an example in the acoustic realm or the mechanical realm would be a microphone. It's just receiving the signal from your voice. It's not sending out anything. It's not sending out anything and waiting for it to bounce back. You just speak into it, and it, through a transducer, it digitizes it, records the signal, and then, the thing on the left is a PIR sensor. That's a passive infrared. So it's in the electromagnetic spectrum, sensing the infrared radiation that everyone's body gives off. So our eyes can't see in infrared, but everyone, since we're warm-bodied things, warm-bodied creatures, we all give off infrared radiation. And that's what those sensors are sensing when you want to do like automatic lighting systems in rooms. And then, so that's passive. Active sensing, you are sending and receiving the signal back. So you are in charge of both the transmission and the reception of the signal. On the left, I have a air traffic control radar. So that spins around and scans the skies, sending out a signal and waiting for it to come back. And based on what it bounces off and how far away it is when it bounces, it can tell, like, okay, there's aircraft here, 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 here in the sky. And then the other images of a submarine working under what looks like a little iceberg. Similar idea with sonar, sending out acoustic pulses, waiting for them to come back, and based on the time of flight, you're able to tell about what objects are out there. And so research areas in sensing, there's sensor, or in remote sensing, there's sensor hardware design, and that's actually creating the sensors, creating sensors that do new things relative to what's already out there, like say a new fancy mic that picks up greater spectrum of frequencies, or a new radio that's able to cover more frequencies or dynamic ranges. This sort of thing will involve a lot of physics. This kind of research will be on the, much more on the physics side, device design side. In current electrical and computer engineering, it's a lot of like semiconductor research, it seems. And on that, so sensor algorithm design is the next sort of research field. That's like, how do you take the data from the sensor and do useful things with it? So there's sort of simpler algorithms that are developed, where there's not a whole lot of processing or relatively complex math that needs to be done. So like fast Fourier transform is an example of that, to very complex things where you're taking raw data and you're trying to make it into a complex decision. So like a machine learning network that, say, takes a radio signal in and then has to decide where to point the antenna for that radio system to get the best signal. That might be a more complex example. And third, we have sensor application design. It's more of what I'm looking at. So that's taking sensors that exist and trying to apply them to new application domains. Example of this in recent years are self-driving cars, where we have things like LiDAR sensors and millimeter wave sensors, which are what I'm currently working with, where they're being used in self-driving cars as a way of enhancing the camera system. So there's the camera portion of the self-driving car, but you also want to be able to tell where the car is at in inclement weather conditions. So LiDAR and millimeter wave sensors, acoustic sensors, are being used to, or applied there to solve that problem. And finally, sensor fusion kind of is falls in line with the algorithm design, but it's taking data from multiple sensors. So if you have a lot of sensors, or you have a lot of different types of sensors, like I said earlier, self-driving cars are a good example of this, because they'll take camera sensors, LiDAR sensors, millimeter wave sensors, just a bunch of different kinds of sensors, and fuse that data together. Very, very machine learning heavy. Very interesting. So this next portion of the, this will start the portion where I talk about the kinds of sensing that I've been involved in the past, and I apologize for the change in style. I took these slides from a previous presentation I did and didn't have time to format them and to format them like the previous slides. But what I'll be talking about is some research fields I've touched on in passive Wi-Fi sensing. So essentially what passive Wi-Fi sensing is using ambient Wi-Fi signals to infer information about the environment that we're in. So the Wi-Fi that's coming from your phone, well, kind of your phone, but more likely your local router, because that's a much stronger signal. Using that signal to do things like target localization, activity recognition, fall detection, and vitals monitoring. Vitals monitoring being things like heartbeat, breath rate. Taking that and using it to accomplish those tasks. Some advantages of why you would want to do passive Wi-Fi signal sensing. Passive Wi-Fi sensing. Wi-Fi signal sources are common. It's very hard in like a modern setting to find a building or an office space, hospital space, space where this might be useful, where you're not going to have Wi-Fi signals propagating and permeating the space. As you and I sit here, there are Wi-Fi signals passing through our bodies, interacting with us, bouncing off us, and potentially going somewhere where they could be sensed and made and put to good use. So, and then part of that, RF signals in general, so which Wi-Fi is a radio frequency signal. They penetrate objects really well, so it enables you to do sensing on the other side of walls for non-intrusive sensing or secretive sensing, depending on what government agency you work for. It works in the dark, unlike visible light, so don't need to have the lights on. And someone said earlier, it's privacy oriented. The resolution of Wi-Fi sensing, the resolution that you can get from any sort of electromagnetic sensing is related to the size of the aperture you have and the wavelength that you're at, but it's also completely limited by something called the diffraction limit. So if you're using Wi-Fi signals, they have a 12 centimeter wavelength. So 12 centimeter at 2.4 gigahertz, the maximum size of object you're going to be able to differentiate is 12 centimeters about, roughly. So that means if you're able to do rough imaging of a person on the other side of a wall, the best you're going to get is a blob, a blobbish form of their figure. So you will be able to know what's going on, be able to tell maybe they've fallen, tell what their heartbeat is, those sorts of things, but you're not going to know like their intimate facial features or those sorts of things. So it has its advantages in the realm of privacy. And so the related work I'll be getting into, there's two that I'll be going over. One is called channel state information that's used to accomplish this passive Wi-Fi sensing. I'll be abbreviating that as CSI. So when I say CSI, just know I mean channel state information. And the other is passive Doppler. And that's similar to Doppler radar, like you might hear weather Doppler radar used in the Weather Channel or whatever the Thai version of that is. But passively and using Wi-Fi signals instead of actively generated Doppler signals. So channel state information. Channel state information takes advantage of a feature of the IEEE 802.11 standard. And the IEEE 802.11 standard essentially says how Wi-Fi is structured. Like what is allowed in Wi-Fi, what frequencies are allowed, what bandwidths are allowed, what channels will be where. It's kind of like the Bible of Wi-Fi. It tells you what's what and what you can do. So it's part of that. And what it is it's information describing the RX, DX, RX is receiver, TX is transmitter. So the communication link between a receiver and a transmitter. So basically how this works is you have a receiver shown on the right and a transmitter shown on the left. The receiver wants to know information about where the transmitter is. It wants to know CSI information from the transmitter. So it sends a CSI request, and the transmitter will send a response. And so basically you have a transmitter response that's encoded. It has a amplitude and a phase, and you receive it at the receiver. The amplitude will have changed because there's distance that the signal has to travel. The signal will have bounced off of multiple objects, causing multipath fading, other things I won't get into, but that'll cause a attenuation of the signal and also a phase change. And so what CSI does is it says, what's the ratio between the received signal and the sent signal? So how much attenuation do we have in the channel, and how much phase change do we have in the channel? And so that's your CSI value per channel, and it'll provide that info per RxTX pair. So if you have here we have 3 transmitter elements and 2 receiver elements. So that's 6 RxTX pairs. So 6 receiver transmitter channels, physical channels, spatial channels that you can think of them as. So per spatial channel, per OFDM subcarrier, which OFDM is a modulation scheme that's used to split basically a 20 megahertz band that you have for Wi-Fi into a bunch of tiny little bands, tiny little channels. And so if you have 3 transmit elements, 2 receive elements, and then 30 OFDM subcarriers, 30 subchannels basically per band, that means for every CSI sample, or for every sample you take using the scheme, you'll have 180 different values, 180 different signal attenuation and phase change pairs. And so the way that we actually use that is a big data approach. We take that and we'll put it in a matrix, a CSI matrix, and we get one of these matrices for each time sample. So say we sample 10 times a second, we want 10 CSI samples per second. We're going to get that 180 times 10, we'll have 1,800 different samples per second of data that we can use to deduce things about the environment. So the benefits of CSI, it's a large volume of information per sample. You get to learn a lot, and the channel characteristics in that phase change and attenuation, it'll encode information about the environment, because for that to happen, different signals have to bounce off of different things. So as a person moves through a space, they're going to change the multipath characteristics of the environment, and the CSI matrix will change in tandem, right? But the thing is for you or I or any human, it's inscrutable. It's absolutely inscrutable. You can't look at the changes in a CSI matrix from one moment to the next and say, oh yes, that's a person moving from here to here. Yeah, of course, unless you're like, I don't know, I don't think so. I don't think it's happening. For sensing tasks, right? To say things like someone's moving or this is over here. What it was originally designed for was saying like, okay, this channel is no longer very good because it has this bad attenuation in phase. Let's shift to this new channel. So CSI was originally meant for communications and co-opted for sensing because it has such a rich amount of information per frame. So to do anything special with a CSI matrix, you have to have machine learning. Basically train your model to take CSI and classify based off whatever's happening. Machine learning classifier. And it's not strictly passive. That's another thing to know. I say it's passive sensing, but there has to be just briefly a communication between the receiver and the transmitter, the receiver being whatever antenna you have set up or device you have set up, and then the transmitter being a local Wi-Fi access point. Okay, so next we have passive Doppler. Passive Doppler takes advantage of something called the Doppler effect, which we've all experienced the Doppler effect, I'm pretty sure. So basically what it is as you have an object moving either towards an observer or away from an observer, the wavefronts coming from that object will compress or expand based on, so if they're moving towards you, the wavefronts will compress. If they're moving away from you, the wave fronts will expand. And where this is most commonly experienced is if you hear an ambulance or a police vehicle approaching, you'll hear like the sound of it get higher in pitch. The pitch increases as it's approaching, and then after it passes you, you'll notice that the pitch starts decreasing as it moves away. So, and what that is the compression and expansion of wave fronts. So, and it only occurs with moving objects. So Doppler specifically lets you pick out movements, movement in signal. And so it's most commonly, we experience it in sound, but it also happens with electromagnetic waves. I think in radio astronomy, if you ever heard of background microwave radiation or the red shift, that's an example of it happening there. Passive Doppler radar takes advantage of it in the microwave spectrum for Wi-Fi frequencies. So essentially how it works is we have this picture here of a room. Here we have a guy, a Wi-Fi access point off to the left, and then a PC with 2 receivers set up. So one of these receivers is known as the reference channel, and that's going to be pointed directly at the Wi-Fi access point. So you can know the signal coming in from the Wi-Fi access point in its, I guess, purest form without any Doppler shift beforehand. Like, what is its frequency? What is its composition? And then the next channel, the other receiver, is what's called the surveillance channel. So you're surveilling an area, and it will be able to tell where moving objects are in the area. So since you're looking for Doppler shift, you're looking specifically for that wavefront compression that happens as someone moves in the presence of the transmitting Wi-Fi access point signal. So let me think, how can I put this? You look at the signal from the reference channel, and you look at the signal from the surveillance channel. The signal from the surveillance channel will be Doppler shifted by bouncing off the moving object in the environment. The signal from the reference channel will not be Doppler shifted since it's a direct link between the Wi-Fi access point and the reference channel receiver. So by taking the difference in those, one will be frequency shifted because of the Doppler shift, and the other will not. You can take the difference and know, okay, this is the Doppler frequency of that moving object, and thus you can say there's an object moving into space somewhere and it is moving at, I don't know, 1 meter per second, and you can use that. So it's really sensitive. So I say sensitive here because it's really sensitive to that reference channel. The reference channel has to be very clear and very isolated from anything else happening in the environment. So usually the way that's accomplished is the receiver will have a very focused antenna or some way of focusing it, so it's just pointed directly at the Wi-Fi access point. And so here's an example of a Doppler spectrogram. This is that Doppler shift I was saying, that frequency difference calculated in hertz over time. So a positive Doppler shift, so an increase in frequency, indicates that the target is moving towards you. A negative Doppler shift, or a decrease in frequency, indicates that the target is moving away from you. And then over time, how that fluctuate is going. So this is actually a Doppler spectrogram of the same situation I described previously, but just someone moving back and forth in a room. So they're moving towards the receiver, they're moving away from it, and thus you see this oscillation in the Doppler spectrogram. And the way we might use this is we might take a window of this, so a small time window, and insert that into like a neural network, a machine learning classification algorithm, and then use that to say, okay, this is what the movements, what walking looks like. And so we can classify walking, or we'll have someone dance in place and be like, this is the pattern of someone dancing in place. So then you can classify dancing, you can classify falling, squatting, different exercise activities. Yeah, so last thing, passive Doppler naturally filters static objects. So since it only works on moving objects, just static things in the background aren't going to affect the Doppler signal. You're not going to be able to get a Doppler shift out of them, so they're not going to matter in your assessment. So that's kind of nice if you're doing human sensing or like occupancy sensing or trying to tell what someone's doing, because in a normal room, people will be the only things moving. or animals, but yeah, that's all you have to really count on in like an office or hospital setting. Compared to CSI, it is truly passive. You don't need to send out any signal. You can just have, you just need to listen. It requires you to know something about the environment, like you need to know where the Wi-Fi access point is beforehand. But beyond that, no signal, passive. The data that you get out of it is somewhat human readable. Like I said before, you can look at this and say like, oh, okay, I can see there's movement back and forth, or like a shifting of forward velocity and then backwards velocity, forward velocity and backwards velocity. But it's still, and all the best methods using this still use machine learning to accomplish anything useful. So difficulties of doing passive Wi-Fi in general, you have limited information about the transmitter since you are, by definition, is passive. You're just listening, so you don't know exactly things about the transmitter unless you have a really specific setup to the situation or you're controlling the transmitter, at which point I would argue that it's not really passive anymore. So without knowledge about the transmitter, you don't know anything about the signal time of flight. So how long did it take to get to you? Because you don't know when it was sent out. And because of that, things like distance can be ambiguous. Distance of objects in the room can be ambiguous. And another thing, Wi-Fi setups vary from location to location. So what I mean by that is one room's Wi-Fi router setup will be different from another. So like where you have your router in your home versus where it is in the office versus where it is in different rooms in the same office might vary a lot. So if you're trying to do something like make a commercial product out of this, it can be pretty difficult to make it work generally. Like you can get good results. And we had research where we would take basically raw signal in from the environment using a small antenna array and some software defined radios, and then put it through a classifier. And we had good results for activity classification for things like I mentioned earlier, like squatting, sitting, falling down, walking, not being there in general. We had good classification accuracy above 90%, but it would break as soon as we changed rooms. And so that was kind of like why we shifted our research direction away from passive Wi-Fi. Yeah, essentially every new environment that you go to needs to be learned. So the system is brittle. It's narrowly focused, brittle, yeah. And so moving on, my current research, because of the problems we had with passive Wi-Fi not being able to because of the brittleness basically and difficulties of working with only receiver-only architectures, I wanted to transition over to using a transmitter somewhere where a platform where I could control the signal transmission and the signal reception. So thus millimeter wave sensor research. Currently doing millimeter wave sensor for motion capture. When I say millimeter wave sensor, that's a whole ultra wideband radar packaged on a chip the size of a coin. So this little black square on this board down here, that's about the size of a, I don't know, like a 10 baht piece, not even that big. So all of that, tire radar, tiny, portable, relatively cheap. So I'm working on applications of that. And it's nice having the greater control over the signal and the environment, or mostly over the signal that's being sent out. So yeah, and that kind of wraps up my little presentation. Okay, I guess we're skipping our Q&A section. So thank you for joining me.
Okay, welcome back to me. Okay, because your presentation is really clear, so yeah. So let's move to our session. Let me share my screen. Okay. Okay. Okay, before we go, let me tell you that the application for the acoustic program is still open until April 8, 2022. This is how you meaningful ideas by sending us a video with your thought for future AI. You could win the ARCE scholarship worth up to 2 million baht. And don't miss. Okay. An active recruitment, a good chance to get to know the ARCE program and learn more about whether ARCE curriculum, scholarship opportunity, R&D projects, and many more. Just scan QR code showing for registration and meet us on April 2nd, 2022. And for those who are interested in studying ARCE but still have some questions, don't worry. This session aims to facilitate students with that step of completing the application from the ARCE program. The session consists of information about required documents and how to complete the application. In addition, the session also provides information about the ARCE program and the pathway to their higher education and future career. And thank you for joining us today. I hope this talk you enjoy this talk, and please stay tuned for the next episode and see you next time. Bye bye.
พี่ครับขอดูสไลด์ก่อนหน้านี้ได้ไหมครับไม่ทันครับถอยอีกอันครับผม
เดี๋ยวจะมีเรคคอร์ดให้นะคะเดี๋ยวยังไงเดี๋ยวส่งให้ภายหลังนะคะ
ครับผมครับ
ค่ะขอบคุณค่ะ